This is lesson 34 of the Quantum Mechanics, a mini lecture series titled Differential Calculus, Part 2. So I'm going to continue on the discussion of differential calculus from the previous video. So a derivative, as I defined before, is basically the idea of rate of change, how something changes with respect to something else, like time, for example. Okay, so a change in velocity, delta v, can also be written as dx over dt. Okay, so in junior science, junior high school, usually we're typically used to writing change in velocity like this. As you approach senior high school, you'll see that velocity can be expressed like this as well. Okay, it's the rate of change of position with respect to time. Okay, how your position changes over time. So now let me show you how the derivative is defined with the help of a graph. Okay, some of you might be familiar with this from senior high school, but for those who aren't familiar with it, let me show you how it's done. So suppose I have a graph of some function. Let me draw a set of x and y axes. Let's say it's like half a parabola. Looks something like this. With the equation of the parabola given by, let's say, f of x is equal to x squared. Okay, f of x can also be written as y. Okay, but I'll just use f of x in this case. So let's choose some point on the graph with coordinates x, f of x. Okay, so x is the x value, the horizontal distance. F of x is the y value. Okay, right off the vertical distance, vertical axis. Okay, and f of x just stands for function. F of x in this case is just a function. Okay, it's in maths, a function is like a machine which takes an input, let's say x, and gives out an output y. So suppose we then decide to shift this point. We'll shift it some h units to the right. Okay, I've used h here, it's just an arbitrary quantity to the right. So we'd end up with x plus h, right? Because x is the vertical distance, horizontal distance here on the x-axis. If I shifted h units to the right, I'm adding h to it, right? So it's x plus h. So if I put x plus h into this, well, I should say, f of x, if I do this, so fx plus h, okay, because the x has been shifted by h units to the right, the f of x becomes f of x plus h, right? So it ends up here. That's our new point. So let's now suppose that we want to determine the rate of change of this shift, okay, in h for this function. So how would we do this? Well, the starting point will be to first work out the ratio of the change in y values minus the change in x values. And the h, okay? So f of x plus h minus f of x over h. This is essentially the slope, okay, or the gradient of the graph. So in other words, the difference in the y values, okay, you've got f of x plus h up here minus f of x. That's why I get this top expression here. And the bottom, the horizontal distance, the change in values is h. So that's why h is at the bottom here, just working out the slope. To turn this expression into a derivative, okay, the derivative of the parabola, we need to write f of x as being equal to this expression. Okay, so f dash x, or f prime, in other words, also known as prime, that just means the derivative of f of x, the derivative of the parabola. That's equal to the gradient, f of x plus h minus f of x over h. But we also need to add something else. We need to make h very, very small. In fact, we need to make sure it approaches 0 so as to be able to get the precise rate of change of the function between the points f of x and f of x plus h. The way we do this, we introduce this lim h approaches 0. So lim stands for limit, okay, limit for short, as h approaches 0. That's what that means. So we need to take h to approach 0 for it to vanish to work out the rate of change of the parabola very precisely. And I'll show you in the next video how to calculate this with the parabola.